So we're taking a look at another one of these where how can you figure out what the derivative is? And we've taken a look at a number of these where there's tons and tons of different ways to be able to find the derivative. And we were looking at, okay, how can we be creative? How can we change the form of it in order to make it work? Things like that. This one is the same kind of thing, except that there actually are not as many different ways that we can go about doing it. But I do want you to see, can you be figuring out what is at least one way you could do this? Because this one requires thinking about it in a way that maybe we haven't actually done together before, or at least not this specific series of steps, even though you know all the skills and we practiced all the individual skills involved. As I walk around, I'm starting to now see that some of you are finding a way through it. The people that are actually starting to find some success, though, I think it's probably because they recognize the issue. What makes this problem harder to do than a lot of the other ones we've done and seen? It's to the power of x, and not just it is to the power of x, but x is to the power of x, right? If this was x to the power of a number, we could do it. That's just like x cubed, right? Or if it was a number to the power of x, we could do that. That'd be like to the power of x. We could do that. But you've never done one that's just x to the power of x. So as you take a look at it, the problem is that we have x raised to the power of another x. So it's the exponent that's causing us a problem. So think about, what can you do to this? How could you manipulate this equation so that you no longer have the x in the exponent up here? There's a couple steps that we could take that are going to help get you there. All right, so let's now come together and see, for those of you who haven't yet thought of a way to do that, well, we have x to the power of x. Now, I got to touch on a couple things that I saw that aren't quite going to work. I saw a few of you who said, okay, well, the derivative of x is 1, and the derivative of x is 1, so isn't it just 1 to the 1? No, it's not. Because that would just be saying that we're just finding the derivative of x only. But it's not just the derivative of x, it's the derivative of x to the power of x. Otherwise, we could argue that any equation involving x was just going to always equal 1 when we took the derivative, no matter what it was. And so we got to actually find a different way through this. And so in order to do that, I only know of one way that I can take an exponent out of that. Well, at least other than taking like a root. And we can't really do the x root, right? That would be kind of messed up. We're going to run into trouble if we do that. So instead, what if we took a logarithm of both sides? All right, now there's a couple different ways you could do this. You could actually do log of both sides. I saw some of you do it that way, where you're doing it log base 10. Or you could be doing it as natural log of both sides. Now, knowing that we're going to be finding the derivative, which one of those has a simpler derivative? Natural log, right? The derivative of natural log is just 1 over x, whereas the derivative of log is 1 over x natural log of 10. And so just to reduce the clutter overall, I'm going to stick with natural log here. So I'm going to go ahead and take the natural log of both sides of this one. So what? We did the natural log of both sides. Why would we want to do that? Why would we care? Because what happens with an exponent on the inside of a logarithm? Yeah. I can move that out front. I can multiply it, right? So this can become natural log of y equals x times the natural log of x, where this x became this x right here. So knowing that, it is now in a form where you can take the derivative using what you already know. It is really at this point, once we've gotten only to here, that we could actually start thinking about how we could be creative about solving this. So we could go through lots of different ways where we could like try to change the form of this, like change it into, instead of product rule, we could try to make it so that it was using quotient rule or something like that. But of course, all those are going to be much more complicated. And this is the first time we've done one quite like this, so I'm going to focus on solving it just through kind of a straightforward method. Then we can worry about creativity after that. All right, so if I'm going to now find the derivative here, I got to do it implicitly. So it's going to be natural log of y. So the derivative of natural log of y is going to be 1 over y, but then it's chain rule. So I still have to multiply that then by y prime. many of you, after you've done a few of these and you're doing the derivative of natural log of y, you might get to where you just write that then as y prime over y, because you just get used to it so well. That's perfectly fine. It does obviously mean the same thing. All right, then on to the right side. We're going to do product rule here because this is x times the natural log of x. So then it's going to be original times derivative. So then that's going to be times 1 over x. Then plus derivative of x, of course, is 1, times original natural log of x. And so this is actually looking like we can clean it up a little bit, though, doesn't it? Because, like, on the left side, yes, that is y prime over y. And on the right side, x times 1 over x is just 1. Plus, and of course, 1 times the natural log of x is just going to be natural log of x. So this is actually looking pretty simple. The only thing that we're running into as a potential stumbling block here is that I still need it to just be y prime equals, instead of y prime over y. So all we got to do is multiply both sides by y now, right? So I'm going to go ahead and multiply both sides by y. So that gives me y prime equals y times the quantity, 1 plus the natural log of x. If there's any mistake that I'm going to see right in this kind of an area, it's going to tend to be that somebody forgets the parentheses. And of course, if you leave off those parentheses, it means something fundamentally different. So do pay attention to that. All right, so this is pretty good. We took our derivative implicitly. There's just one little thing that I'm not quite happy about on it, is in terms of both x and y. And yeah, oftentimes we end up with an equation that's in terms of both x and y on these. But this doesn't have to be. It's really easy on this one to make it only in terms of x. Because what does y equal? X to the x, right? So this would be really easy to change that out. So we're going to go ahead and do that because it is so straightforward. So we're going to go y prime equals x to the power of x times 1 plus the natural log of x. And if you want to distribute the x over x in, you can, but you really don't need to. So this is typically how we might leave our answer in this kind of a format. So this one is now complete. That is the correct answer here. Notice how we did this, though. This is actually a particular method of finding a derivative, and one that we're going to be spending a little bit of time on here in the very near future, where notice that because the x was in both the base and the exponent, we had to start by taking the logarithm of both sides. And yes, you could have done this with just log instead of natural log, but why? That's just going to add complexity to it. So I would just take the natural log of both sides. And the whole reason we do that, remember, is so that we can take that exponent and we can pull it out front. This method is called logarithmic differentiation because we start by taking the log of both sides and then we find the derivative from there. So again, logarithmic differentiation is this technique's name. And we know we need to use it. You notice I'm trying to create a big pattern here, re-emphasizing these points. We know we need to use it when you have x in your base and x in your exponent. When that happens, that's the only way to get around that.